Welcome to Chapter 2 of the Creating Lighting Fixture GDTF video series. After completing the light's description in the last chapter, this chapter continues by looking at the setting up of the geometries of a light and how they link to each other and the physical attributes of a light. As with the previous chapter, you can jump to the specific sections of this chapter using these timestamps. Before we go any further, it's important to know the difference between geometries and models. Models describe the physical shape of the parts of a light or device, such as the yoke or the base. They are used to create the geometries, which in turn are the building blocks used to define how the light is assembled and how the physical attributes of the light map to the GDTF. Good examples of this are that pan links to the yoke and tilt to the head, just like in the real world. The geometry section of the geometry tree defines the structure of the light, using a parent-child system to show how the parts of the device are joined to each other. The conventional and moving head templates provide good examples. The top-level geometry is the parent, and each child that is linked to it is shown as an offset row underneath. As you can see, both follow the same standard. They are drawn as if hanging ready to use. In the case of a conventional, the top-level geometry is the yoke, whereas for the moving head, it's the base. There should be a child geometry for every part of the fixture that has physical functions of the light associated with it. So you'll need a yoke for panning and a head for tilting. Remember, a GDTF has to include at least one geometry for the file to be valid. Let's start adding geometries for our example light. We'll continue from the previous save in the builder. First, open the Models tab and start adding the models for the different parts of the light. Make sure to name each of these as you import it. You'll need GLB files for the base, yoke and head. If you have 2D SVG files for the top and section side views of the light, you would add these at the same time. You'll need to create some custom models for the lens and pigtails. The lens will be a flattened cylinder, and the pigtail has to use the pigtail primitive. Now that all the models are prepared, we can use them to create the geometries for the different parts of the light. It's time to start defining how the parts of the light relate to each other. Open the geometry tree and hit Add Top-Level Geometry. The top-level parent object will be the base. Choose the base model that you've already created. Since this is the base, it can be left as normal geometry. It's good practice to name the geometries by the physical part of the light or device they represent. Hit Add Child Geometry. After the base comes the yoke. Name it Yoke, and in the Geometry Type drop-down choose Axis. This allows it to turn. You'll need to use the Translate mode of the 3D Visualizer to correctly align the yoke with the base geometry. The head is added in the same way. Add the child to the yoke. Again, set it to use Axis, and move it into position. The lens is a child of the head. This should be set to Geometry Type Beam. Each lens has a variety of properties, which combined with the photometric data in the physical description of the emitters, enables accurate visualization of the light's output in a previous environment. For this example, let's set the lamp type to LED. The power for each emitter is not the fixture's total power requirement. Define the brightness of the emitter in lumens. Like the power, this is only for this emitter, not the fixture as a whole. So if there are multiple emitters, divide the total output of the fixture by the number of emitters. Set the basic color temperature of the emitter, and choose the lens type, in this case spot. Set the beam and field angles in degrees. Beam and field angles can be found in the user manual of your light, typically in the form of a graph similar to this. Here is another way to show the beam and field information. Both the beam and field angles are measured from the center of the light beam. The beam angle is the measurement angle of a light source where its intensity has fallen to 50%. The field angle is the measurement angle of a light source where its intensity has fallen to 10%. Enter the diameter of the light beam at the lens. CRI is the color rendering index of the light. For this example, enter 90. If your light has more than a single light source, for example a strip blinder, you'll need to add lens objects for each light source and position them appropriately in the visualizer. You can quickly duplicate your lens geometry by using one of the duplication commands from the context menu in the upper right hand corner of the geometry tree. The last geometry you need to define is the pigtail, which is used to show where the power and data connectors are on the light. This should be a child of the base, so make sure to select the base before adding it as a child. If you do forget, you can drag and drop it into the correct position, and in most cases will be at the rear side of the base geometry in the 3D visualizer. That's your basic geometries finished, so it's time to add the power and data connectors. These should be added as children to the pigtail geometry. Name this one as power in and define it as a wiring object. Wiring objects are virtual, so it doesn't need a model. Instead, you'll need to define more of the wiring object's attributes in the properties. The component type defines what the wiring object represents and its available properties. Lights mostly use inputs, outputs, and consumers. Since this is the power in, it'll be a consumer. The first group of properties define the connector type and internal wiring. Let's start with the connector type and choose PowerCon True 1. Signal will be power, pin count is 3, and the signal layer is set to 0. The pin count is the number of pins in the connector that are available to use. And all wiring objects on the same signal layer get connected together. Set the orientation to top, as when you look at the fixture from above, the connectors are in that direction. The wire group can be left empty for this example. The next group of properties define the electrical behavior of the device and are only available for consumer wiring objects. All of this info can be found in the light's manual. Electrical payload is the rated power consumption of the light as a whole, as per manufacturer documentation. The operating voltage range, in our example, will be from 208 volts to 250 volts, and the frequency range from 50 through 60 Hz. Cos phi is the light's power factor. For this example, you should enter 0.99. As you can see, individually setting up all of a light's connectors can take a while, especially once you include DMX and Ethernet connectors. A faster option is to open the context menu, choose one of the standard connector configurations, and then customize them. The DMX and Ethernet connectors are pre-configured with connectors, signal, and so on ready to go. Now that you've added these, all you need to do is delete the extra power consumer. That brings us to the end of this chapter. The geometries are set up, and it's time to move on to the emitter and color data for the light. Chapter 3 will go through this process in the physical description page of the builder.